the Metropolis-Hastings algorithm. So let me introduce the problem, okay? So let us imagine that we have a function v. Okay, so this is okay. So maybe for simplicity, let us look at this function only on this interval here. Okay, so the question, one question that people may ask about is to find the minimum of this function v. Okay? So if we have a explicit formula, one-dimensional function v, in calculus we learn how to find this the minimum. Okay, so we say, okay, the minimum has to be a critical point. So we take the derivative of v. We say we take v equals 0, and we check, no, which one of the critical points is the minimum. But this is very important from a theoretical point of view. But if you are looking for an actual algorithm to find the minimum, this is basically you didn't get too far with this idea, because you transform the problem of finding a minimum to the problem to find zeros. Okay, so to find zeros of a given function, again, no, if the function is not a simple function, it's a complicated task. Okay, so there are methods. No, there is for example, Newton method that will help you to find zeros of a given function. It's a possibility. But it's still not really a simplification of the problem. It's just a transformation. You transform one problem into another problem. So something that is very popular is called the gradient descent method. No. How the gradient descent method works? So the idea is that we want to find a minimum here. Let's say we start somewhere here, x0 here, some point x0 here, and we want to find a minimum. So this point is not a minimum because the derivative is not 0. Well, that's one of the reasons. No? I mean, it's not exactly the only reason. So you take x0, and let me call this interval here I. And then in a recursive way, so first we introduce a mesh. So I'm going to explain you what the mesh is in a minute. So here it's minus. If you want to find the minimum, you do minus. If you want to find the maximum, you do plus. So the idea is that here you look at the derivative of the function v. And the derivative of function v tells you on which direction the function is decreasing. So you decide to advance in that direction. Okay? And you advance a mesh H. Okay, so in this, if I'm not wrong, H is here. Okay? So the mesh, the step, the mesh H is the step that this method will use to update your next point. And so you go down in this tangent line a distance h, a vertical distance h, and this point here is going to be x1. And make a mistake here, no? So this is not h. So let me see. Is this correct? Did I make some mistake? No, it's okay, no? I think it's okay, no? Yeah. So this is an iteration. Sim.
É como se fosse vezes H? Tipo, V' é a reta do meio?
É a derivada.
Uma derivada do ponto.
So you see that when in this picture here, you're going to go down, and when you get close to the minimum, what will happen is that the derivative starts to be close to 0. So when you multiply by h, you get a very small difference between xt plus 1 and xt. Okay? And so the observation is that
Maior força derivada, mais ela pesa.
mhm. So under some conditions, okay, so I'm not going to explain the conditions exactly, but what happens is that xt converges to, it doesn't converge to the global minimum, it converges only to a local minimum. Let's say x infinity. Okay? So what are the conditions? So imagine that h is very big, okay? So it's like big. Then when you do this iteration here, when you do the step, what is going to happen is that you're going to pass to the other side. Then you iterate again, you pass again to the other side, you don't converge. Okay? So if this mesh is too big, you don't converge. If the mesh is very small, this method is guaranteed to converge to a local minimum. But if the h is very small, it will take ages to converge. So there is a trade-off between the risk of not converging and the time it will take to converge. Okay. Well, this is what is called the gradient descent. It's you can do it in any dimension. Okay, so in higher dimensions, what you do is that xt plus 1 now is a vector. I'm going to be xt minus, now the function v is going to be a function from Rd to R. Therefore, the derivative is a gradient. So now what you do is that you take multiply h by the gradient of v at the point h. And this gradient here is the gradient in the name, and the minus here is the descent on the name. And, therefore, what happens is that, well, and this is the idea. So this thing here, when h goes to 0, actually it's a numerical approximation. Observation. This is the sequence ht, no? Is a numerical approximation of the ODE of the ODE here, of this ODE here. Okay? So this ODE here has as stationary points the zeros of the gradient of V, and these stationary points are divided in attractors, repulsors, and saddle points. And the attractors are exactly the local minima of the function V. So the solutions of these equations are attracted to the attractors. So they go to local minima. And the problem with this method is that it goes to a local minimum, meaning that if you start here, so here we have x infinity, then you go to x infinity till that, to a different minimum, and you will get stuck in that minimum forever. You will not find the local minimum. Okay. So there is a variation of this so let's say drawback, no? Okay, so one possible way, it's not the only way, no, but one possible way to address that problem is to if you want to do this same algorithm, start whenever you reach a local minimum, you start again from a different place, and you decide in some way which are the places at which you are willing to start. You start in these places, and you let the chain run, the algorithm run, and you may or may not find all the local minima, and once you find all the minima, you can evaluate V and decide which one is the global minimum. But there is another way to do this, which is very popular, which is the stochastic. Gradient descent. Okay? So in the stochastic gradient descent, you do the same thing. You start at zero. Let's say in a domain D, Okay, so maybe not an interval, it's something higher dimensional. Then you do the following. You define xt plus 1 as xt minus v prime ht times h, the same as before, but you add a random number xit where these xits are IID. Okay? So they have to be at IID. If you are in RD, it has to be something that has positive probability of being pointing in at least all the directions. Okay, so here, depending on the context, you can choose something different, whatever you want. Okay, usually when the people is doing numerical analysis, you start discretizing space. So you have a grid. So the natural thing to do here is to take this as some sort of discrete random variable. So basically what you do is that you choose one of the 2D canonical vectors, uniformly random. The number sigma here is a small parameter that is sometimes called the temperature of the algorithm. And the idea is that the higher the temperature, the less likely this algorithm is to get stuck in a minimum. And the smaller the temperature, so the higher temperature is more random. And the smaller the temperature is less random. So if it's less random, it looks like the original one, so you got here. You don't stay here forever because there is something random, but you oscillate around this point for a long time. And what may happen at some point is that there is a very small chance that you start to climb this hill up, and then you go to another minimum. Okay? So this is called the stochastic gradient descent, and this is a discretization. Now it's no longer an ODE, but it's an SDE, so it's a stochastic differential equation. Whatever it means. Okay, well, this thing here is a Brownian motion. Okay. In all of these methods, usually the number h and the sigma here are not fixed. Okay, they are adaptative. So if you are in regions on which the grain is very, very big, you don't want to take an edge very too big, because you are going to make jumps which are too big. So then, so sometimes here you put an edge that depends on the size of v prime in some way, to make it to make the algorithm be a little bit more careful when the grain is too big. And also, when the algorithm hasn't converged yet, maybe you don't need the randomness. Maybe you just need randomness to help the algorithm to get out of local minima. When you are close to a local minimum, you make the algorithm more random, so then you go to another minimum. Okay, so there are various variations that you can do with this. It's a very simple algorithm, and the advantage of very simple algorithms is always that you can modify them in many, many ways that you may imagine. Okay, so now I'm going to show you a type of function, okay, which appears a lot in actually practical problems. Okay, so I'm going to consider the space. So I'm going to fix n, a natural number that we want to think about as big. I'm going to define omega n. So omega n is our classical minus 1 plus 1 to the n. Okay, so it's the space of binary sequences of length n. We're putting minus 1 and plus 1 just for convenience. It could be 0, 1 if you want to, it doesn't really matter. Now we are going to define a function, we usually call it j, which goes from n cross n to r, and I'm going to define a function v. V of sigma, so sigma is an element of this guy, so it's a binary sequence. So this is the function for which I want to compute the minimum. Okay, so just to understand what this function means, so imagine that g is constant, equal to 1. Then v is the sum over I and j of sigma I, sigma j, which is the sum over I of sigma I squared. Right? So what is the minimum of this function here? It depends on, actually depends on whether n is even or odd. But if n is even, is 0, because you can take plus minus plus minus plus minus and then gives you 0, right? And so let's think about n even, yeah, so we don't get complicated. So the first thing is the minimum is 0. But there is something peculiar about this, no? Because what are the minimizers? What is the minimizer? Actually, there is more than one. You see that the minimizers of these functions are all binary sequence with the same number of pluses and minuses. So how many of them are? Is 2n, choose n. Right? I think. No? Because, yeah, it's... how can you put n eggs in 2n baskets, no? So it's 2n choose n. So the number of elements of our space is 2 to the n. The number of minimizers that actually realize the minimum is 2n choose n, which we know is of order, you remember? There is some stirling to do, but it's of order, is more or less like 2 to the n divided by square root of n. Okay? So basically, in a huge space of 2 to the n, 2 to the n divided by square root of n points are minima. So this guy here has a lot of minima. Okay? So let's think about now what happens if g is equal to minus 1. Okay? If j is equal to minus 1, then v is equal to the sum, to minus the sum over I and j and sigma I sigma j, and this is equal to minus this sum here. So in this case, the minimum is minus 1, minus n squared, right? Because I take all these guys equal, and the number of minimizers is 2. Okay? So the behavior of this function is dramatically different depending on the sign, which is okay, because you see, if it were a one-dimensional function, it is like so we have in the first case, it's like it is a parabola like this, then the minimum is the minimum. But in the other case, when j is negative, it's like it's a parabola, inverted parabola, and then the minimum is going to be one of the points at the boundary. And so, yeah. Why this is a sort of relevant problem, okay? Because usually this, see, yeah?
Você disse que esse gradiente estocástico ele ficou oscilando e depois ele tem probabilidade de sair igual. Mas por que? Eu não diria ir para estacionário? Porque ele pode sair.
Porque aqui, se por exemplo, por algum motivo, isso aqui sempre aponta na direção oposta do V, do gradiente, ele vai sair. Ou seja, se o xídet é aleatório, então pode ser que ele aponte para cá. Se ele apontar sempre para cá, você vai, a cada passo, depende do valor de H e de sigma. Vamos pensar que o H é muito pequeno e o sigma é só pequeno. Na prática, usualmente, sigma é da ordem de raiz de H. Então é bem maior que H. H é muito pequeno e sigma é pequeno. Ou seja, por exemplo, H é 0,01 e sigma é 0,1. Então, o que vai acontecer é que se você tiver uma... em geral isso não acontece, que a aleatoriedade ela é coordenada, porque como é aleatória, às vezes aponta para lá, às vezes aponta para cá, Então fica oscilando. Mas algum dia, ela só vai apontar para lá e vai fazer o processo sair.
Aí você corrige, por exemplo, os mínimos do local, então vai ficar menos tempo. Os mínimos do global.
Ainda, quanto tempo vai passar em cada mínimo é outra história.
E isso aí não é um modelo de spin aqui.
Hã?
O problema não é o modelo de spin, o modelo de...
Sim. É um tipo de modelo de spin. Não é um modelo de Ising, mas é um tipo de modelo de spin. Se chama vidro de spin. Spin glass. Sim.
As sequências são de tamanho 2n?
Aqui sim, porque aqui era para que fosse par. Então, na verdade, aqui o que estou pensando é que o n grande é igual a 2 vezes n pequeno. Na verdade, isso aqui é da ordem 2 a 2, né? Se vocês fizerem o estilo incorreto. So, yes. So, what this Jij represent? Okay, they represent correlations usually. Okay, so this is what this thing is trying to do here is trying to model a random function in a sense. Okay, so you have a function, you want to learn about this function, and you start to measure this function in different points, and these measurements, they have correlations. Okay, so this is something that is very in a sense, it's something very typical in machine learning. What you're trying to do is to learn this function p, and what you do is that you start to do some computations, and this is what you have access, the correlations. So now you learn your function v, and then you want to minimize it. Right? So it's a very classical optimization problem. You are in the stock market. These sigmas represent some sort of stocks. These j's are the correlation between stocks, and then this function here will be something like some sort of cost function that you want to minimize. So in many problems, this type of things appear very naturally, and then you want to minimize this function. This function is very difficult to minimize, okay? Because what happens with this function is that it's full of local minima. Okay, so people try to they do just to model this function. For example, sometimes what people do is that they choose this Jij random numbers. Okay, so random numbers between -1 and 1, just to see what happens. Okay, and what happens is that you get a function which is full of local minima. So when you draw, if you try to draw a picture of this type of functions, what you will see is like a mountain chain, no? Full of valleys and peaks, and this type of functions is for those type of functions, the deterministic gradient descent gets stuck basically at each step. So you just run a few number of steps and you get stuck in a minimum, and then you have to reset your thing and you get stuck again. So it's so your algorithm doesn't really doing anything. If we come back to the original idea, on which we say, okay, so we run the algorithm until we get to a minimum. Now we start at a different point and we run it again until we get a minimum, etc. And we get a collection of minima, and then we verify which of the minima is the global minima, then so you do that. And you explore in some way, you define, okay, I'm going to start, I don't know, they have an interval or maybe a rectangle, and you do a mesh. No, so you divide on a grid, and you start at each point of the grid, and you run this algorithm. So what is going on is that you try to do something like that for this function here. Your algorithm will run like 5 steps and then go to a minimum. So it's not very different from just sampling at random. So this is the function, and then and now we want to find the minimum of this thing, okay? So idea. So, and this is the key idea. So this idea is the Monte Carlo method. Okay, Marco Shea Monte Carlo is modify the random walk. Notice that this omega n is just the hypercube, okay? So up to here we have analyzed the random walk on the hypercube, but with a lot of detail. So we know, for example, that the mixing time is of order 1/2 n log n. Something like that. Well, maybe we don't know, but there was a question on the exam about that. And the random walk on omega n will try to explore and find the minimum. That's the idea. So I'm going to call global minima here because maybe there is more than one global minimum, but that's okay because we want to find the value of the minimum, not the minimizer. Okay, any minimizer will work. Okay, so here what we do, we introduce a parameter beta, which is called the inverse temperature. So it's called the inverse temperature because this algorithm it was actually introduced by the physicist, and it's inspired in models from statistical mechanics on which beta is the inverse temperature. So we define mu. I measure mu So we define this measure mu, okay? Okay, so what is the idea? So if beta is very, very, very big, the global minima get an exponentially large, doesn't really, well, yeah. It gets exponentially large weight here, but the points which are not local global minima, they get exponentially larger weight, exponentially smaller weight. Okay, so what happens here is that this measure here, when beta goes to infinity, converges to the uniform measure on the global minimum. That's what's happened. Well, that is what happened. Okay. So because so when beta is very, very big, you see that the function v actually, if you add or subtract a constant to the function v, doesn't really matter, no? Because the minimizers are going to be the same, and I'm just shifting the function v. The minimum is going to be the same again. It's just you just put the constant back if you want. So you can assume that the minimum, the value of the global minimum is 0. So you can just bring the function b up until the global minimum is 0. Okay. This is a little bit it's in practical terms it looks awkward because we actually don't know what the what the minimum is. So how can you just shift by the minimum? But mathematically you can do that because it's just a problem of existence. The minimum exists, so you can just shift it by the minimum. Then v is equal to 0 at that point. Then you can check that in this definition here of the measure mu, that constant doesn't matter because it cancels. So if you add a constant to v, the constant goes out of the expectation as a multiplicative constant. Here too goes out of the sum and cancel. So we can assume that v is equal to 0 at the minimum. If v is equal to 0 at the minimum, the weight of the minimum is 1. And the weight of any other point which is not the minimum is exponentially small. So when beta goes to infinity, only the measure is really concentrated only on the global minimum. When beta is 0, this is a uniform measure. So this measure mu, as beta goes from 0 to infinity, interpolates between the uniform measure and the measure which is which only gives positive probability at the global minima of the function v. Okay, why the exponential function here? Well, why not? It's just a matter of convenience or practicality or tradition maybe, because so something nice about when you do research is just you can do whatever you want. So if things work, then it's okay. Doesn't matter. As long as what you're doing is new and interesting, you can do whatever you want. So the guys that got this idea that when describing are physicists, and for physicists it's very natural to take exponential and not other functions because of statistical mechanics. So this measure, in principle, where beta is large, is concentrated on the global minima. Not completely concentrated, but gives a lot of more weight to the local minima. So it means that if you start to look at your Markov chain, it's going to spend most of the time at the global minimum. So this is what you want to do. No, you want to, because you don't want you want an algorithm that doesn't get stuck in a local minimum. So now what is the, okay, so this is nice, so this is a measure. So now, so we have, I want to modify the random walk on the hypercube in such a way that the invariant measure is mu instead of the uniform. So this is what we want to do. So how do we do that? So let me define the following. Okay, so let me define sigma x So let me define that, okay? So what is this? So actually, this is the allowed moves. This sigma superscript x are the allowed moves of the random walk. So what the random walk on the hypercube does? It chooses as a position x on the binary sequence, then flips a coin. With probability 1/2 it does not do anything, and with probability 1/2 it changes the sign of the binary entry at that site. Okay, so it goes from +1 to -1, or from -1 to +1. This is why I put plus minus instead of 0 1s, because at this point it's easier to put here minus instead of 1 minus. Okay, it's a little bit simpler. It doesn't really matter. Okay. So now that we have this, we see that we have this, no? So the idea is to modify this random walk in such a way that the invariant measure is mu. And what does it mean, modify a random walk? So we always have to think about this on algorithm terms. Okay, so so what we have is that. So how do we do proper programming? No. If you want to really implement this type of things, the first thing that you do is that you create a library, no, called RWN. Okay, so RWN has an entry which is a binary sequence, and gives as a result another binary sequence on which you select one of the entries at random. You erase that entry, and you put 1 plus 1 minus 1 with probability 1/2. Okay, so you first thing that you do is that you create that library. Okay, this is probably already built in most of software packages, no, of programming packages, R, Python, etc. But you could create a more sophisticated RW if you need to. Okay, so this is the first thing you have. Okay, so now we want to construct a Markov chain with measure mu as a measure invariant using our library package, where a nicely defined function RW. So what we can do is that we sample our RW, and then we decide whether we accept or reject the sampling. So this is the classical rejection sampling algorithm using RW as an entry. Okay, so we have sigma t. So we define sigma t plus 1 tilde as RWN of sigma t. So we have a function, no? Which is the rejection function. So rejection. Okay, so we have two libraries, no? So we have a RW and rejection. Okay. So now sigma t plus 1 is going to be equal to, there are two cases. Sigma t if rejection of sigma t plus 1 is equal to, let's say, 0. So now, what is rejection? Okay, so how do we take this decision? So in the examples yesterday, the rejection function was a deterministic function. It was a, so what was this rejection function here? Was just we sample a new point, and if the new point is inside the region D, we accept the point, and if it's outside, we reject it. So this function was equal to 1 if it didn't depend on the sigma t. In omega t, sigma t. It only depended on the new sample. So if the new sample was inside the point, rejection was equal to 1. And we accept the point. Maybe I should call it accept. No?
Aceitar alguma coisa é sempre rejeitar outra.
Hã?
Aceitar algo é sempre rejeitar outra.
Exatamente. Mas só que de forma positiva.
Sim. Aí nesse caso, se for maior, aceita. Se for menor, meio que...
Então, so now that was deterministic. So usually this number here is not deterministic. What we do is the random number. So what we do is the following: is that accept is actually a Bernoulli random variable, and the density of the Bernoulli random variable is a function that I'm going to call big C. Okay? So this is what we do. Okay, this is a general form of a rejection sampling algorithm. Now we have this rejection sampling algorithm, and what happens with this rejection sampling algorithm is that it's modifying the original invariant measure of the chain because the original Markov chain is modified. So yesterday, actually a sequence of IID random points is also a Markov chain. It's just a Markov chain which is very trivial because all the rows are equal. What happens is that the next point of this Markov chain doesn't depend on the current state of the chain. So it's a trivial Markov chain in a sense. A sequence of IID random variables is just a trivial Markov chain. And what we were doing there is that we were modifying that trivial Markov chain in such a way that invariant measure now was the area measure of our domain D. So now what we're going to do is that we did that and we modified it. Okay. So now let's compute the new PA. No, that there is no, so it depends on the function A that I wrote there. I call it A, no? Yeah. No, I call it C. PC. Okay, so if I want to go from sigma to sigma prime, the first thing I had to do is that I had to sample sigma prime. If I want to accept sigma prime, the first thing I have to do is sample it. So that was the original one. And now that I sample it, I'm going to accept it with probability C. And I want the new chain to have as an invariant measure the measure mu. As I've been telling you a lot of times already, to check that a measure is invariant is many times difficult. It's way easier to check whether the measure is reversible. And this is something that we can use to our advantage now, because now the measure is given and the unknown variable is the probability. No, is this PC, which means because this is the unknown, this is the free variable. So we can use the reversibility equations to our advantage as an equation for the p's, not for the mu's. So what we want to do is that we want to mu sigma, p sigma sigma prime has to be equal to mu sigma prime pc sigma prime sigma. Okay? Actually, we only want this. Okay? But let's keep it general. Okay? Because I mentioned that because if this sigma prime is not one of the sigma x that I define there, then this probability is 0. And this identity is trivially satisfied because both probabilities are 0. And then, well, 0 is equal to 0, no, there's nothing to be decided. So if we do this, you see that this probability here is, well, we write what it is, no? So it's the probability of the random walk and here we can already, okay, no, let's do it. We're not going to use the specific formulas until the end, because using the specific formulas we have for p random walk and for mu is not going to help us at this point of the computation. Okay, so this point of the computation does not benefit from the particular formulas of our measure mu and our probability p. Therefore, we're not going to do that replacement right now. So from here you can see that, well, C sigma sigma prime, it's equal to mu sigma prime, PRW sigma sigma prime. So I'm going to do it the other way around, just because of convention. So we have this relation between C sigma prime sigma and C sigma sigma prime, and all the other parameters. So all these parameters are given, are parameters of the problem. This is an unknown. This is also an unknown. So you see, I can choose this guy here basically in an arbitrary way. And the only thing that will do is that it's going to fix this number here. There is one restriction, okay? What is the restriction is that the number C has to get values between 0 and 1, because our nullity of parameter 2 is not well defined. No? It has to be a probability. It's the probability of acceptance, no? Or of rejection, depending on how you define things. So we have a restriction. C sigma sigma prime has to be smaller or equal than 1, and C sigma prime sigma has to be smaller or equal than 1. Okay? So if you assume, if you want to impose that, so we can do that, no? Why we take this equal to 1? Okay, 1/2 also works. Then we have to take this, divide this number here divided by 1/2, no? Because it's had to divide by C. It's convenient to take it equal to 1 because in an algorithm, it's going to be more efficient if we accept most samplings. If you accept more samplings, the algorithm is going to be more efficient. Therefore, since C has to be less or equal than 1, let's take it equal to 1, so the most we can. And then C prime is equal to 1. So if not, if this number is bigger than 1, then what we have to do is that we have to take C. We have to choose the value C in such a way that when you multiply these two numbers, you get something smaller or equal than 1. Again, the best case scenario for efficiency is to choose C in such a way that this number is equal to 1. So then it's going to be the inverse of this number, no? Something funny about this thing here is that if you do this and we compute C sigma prime sigma out of this formula, we get exactly the same values that we get computing using this formula here. Okay? So one can check that this is correct. Okay? So how this is implemented? So first thing we do is that we run a we do this, okay? So we sample a new possible step of our Markov chain. Then we throw a number that I'm going to call A of t, which is a Bernoulli of parameter C, sigma t plus 1 tilde. Okay? So this is the acceptance number. And then we define sigma t plus 1 equals to the new guy if we accepted, and the old guy if we rejected the new.
What's this tilde? I don't get it. It's just,
Just a dummy variable on your algorithm.
okay. What's the difference from doing sigma t plus 1 and sigma t plus 1 with the tilde?
It's a different variable. So you have to think algorithmically. No? You are doing an algorithm. You want to go from sigma t to sigma t plus 1. Then you define inside your algorithm a dummy variable that is going to be just defined inside the algorithm, inside the loop. So you can call it another thing, no? Psi doesn't really matter. And then you run your algorithm, and at the end you decide whether the new guy is equal to this dummy variable or not.
The tilde works like a pulse variable. Like using this, that you do this step in the Markov chain, but you are not you don't need to do this step because you need to calculate it.
So the okay, so this is so first you do your random you take one step on the random walk, then you can compute this number C. Now you can throw a Bernoulli of this parameter, no? And now if the Bernoulli is 1, you decide to accept the new step, and if the Bernoulli is 0, you decide to reject the new step.
Por enquanto, isso é só para mudar da uniforme e passar para uma exponencial, né?
Sim. Na verdade, para mudar aqui, na verdade, RW pode ser qualquer cadeia de Markov que tenha essa probabilidade de transição. E é isso aqui para mudar para a medida mu, que pode ser qualquer coisa também.
A transição ali, claro, com arestas, né? Com vizinhos do interior.
Não necessariamente.
O sigma' pode ser mais fácil, né? X fácil.
Pode ser o que você quiser, na verdade. Pode ser outro espaço diferente. Pode ser outra cadeia de Markov. Pode...
E por que está buscando a exponencial? Você está querendo alguma coisa tipo perda de memória? Alguma coisa?
Não. Exponencial é porque o cara que inventou botou exponencial e ponto. Acabou. E funciona bem.
Mas é como se fosse a variável aleatória exponencial mesmo?
Não.
É só
Não.
a mesma função.
É só a mesma função exponencial, tá aí porque o cara achou que ia funcionar e funciona. Isso.
É um modelo de distribuição da física para que ele está fazendo é fazer um logaritmo para poder achar a amostra daquela distribuição aqui, entendeu? Entendi. Aí ele fez aquilo ali para balancear, aquele mínimo ali, ele vai aceitando.
É para não deixar passar de uma probabilidade. É isso.
É porque confundir um pouco, tipo assim, não faz sentido você tratar uma amostra com uma distribuição. Mas as distribuições já existiam antes, tipo, mecânica estatística foi feita em 1906, 1907, a Cadeias de Markov foi em 1907, um ano depois. Então existiam os modelos de distribuição estacionária.
Se você já conhece a distribuição, também você vai fazer.
Só que achar uma amostragem é difícil, porque são várias partículas.
Então, going back here, okay, this P random walk here is any probability distribution. You could use any stochastic method you want here to run the metropolis hasting algorithm. Okay. What happens is that depending on the context, this random walk may change. Okay. So something that nowadays is very popular is that you can use, your current neural network to build the next neural network, no? So you are going to run this metropolis hastings, but here, this stochastic matrix here will be the stochastic matrix of your current neural network, and the result will be the next neural network. So anyway, so this is a general formula that works for any stochastic matrix and any measure mu. Now, in the case, so in our case, no? Now we can use our particular formulas, no? Remember that PRW of sigma sigma prime is actually equal to PRW of sigma prime sigma, right? No nosso passeio. So in that case, these terms here cancel. And this and mu sigma prime divided by mu sigma, which is the other factor that appears in the formula for the acceptance function, is equal to, it's e to the minus beta v sigma prime divided by Zn of beta, so the normalizing constant, times Zn of beta e to the minus beta v sigma. So you see that the first thing that is nice about this formula is that these constants cancel. These constants are super difficult to compute. Okay, but and it's a very good news. It's very good news that we don't need to compute them because they just cancel. So this number here is equal to the exponential of minus of this difference here. Okay? So this is what sometimes people call the delta. Okay, so it's a difference. So this V here, usually people, especially because this comes from physics, they think of the function V as a potential energy. And this difference here is the energy difference. And that's why they call it delta. So what is happening here? So what this chain does, okay? So if you are going into your next step, if you are going to a configuration with a smaller energy, you always accept that step. Because that's good, because you want to minimize. If you are going to a new configuration with higher energy, you don't reject it always. You accept it with this probability, which is smaller than 1 because the difference is positive, the beta is positive, there is a minus here, so it's the exponential of minus a positive number. So it's a number smaller than 1. So you accept, so you still accept the new step, but with a smaller probability. And this is what allows you to get out of local minimum. Because you don't get stuck at local minima. No, eventually you go out of the basin of attraction of the local minimum. And then if you run this Markov chain for a long time, what you will see is that it's going to spend most of the time on the global minimum, because the invariant measure is built in that way. So this is the Metropolis Hastings, so this is the particular so this is the Metropolis Hastings algorithm. Metropolis Hastings is this choice of the rejection function. There are others, okay? So just
Isso foi criado pela primeira vez para alguma aplicação específica ou apenas mesmo como teoria para minimizar funções?
Então, reza a lenda que isso aqui foi criado, depende da fonte, não? Mas o mito, não? É que isso aqui foi criado para saber se a bomba H ia explodir no mundo ou não.
Aquela história do Oppenheimer.
Isso foi depois do Oppenheimer, na verdade. Teller. Então, a história é que esse algoritmo foi criado por... bom, tem toda uma questão de quem foi que inventou o algoritmo exatamente, mas quando eles construíram o primeiro computador lá em Los Álamos, eles queriam fazer uma coisa que se chama... eles não chamavam ainda de Metrópolis, não em Monte Carlo, nada disso, porque ainda não existia. Então eles faziam uma coisa chamada... como chamava? Dinâmica molecular. Então você tem partículas com interações entre elas e você quer simular o que acontece com essas partículas. Então você simula com algum método. E aí você simula por um tempo bem longo até ver que as partículas entraram num estado de equilíbrio. E aí você estuda esses estados de equilíbrio. Como é que eles são? Qual é a densidade, qual é a velocidade, o momento, a energia, etc. Isso se chama dinâmica molecular. Então isso foi o que os caras queriam fazer. E rapidamente chegaram à conclusão que isso aí não dá certo. Porque o tempo que você tem que aguardar é longo demais. E aí o que os caras fizeram? Disseram, bom, vamos tentar acelerar a simulação botando temperatura. O que quer dizer botar temperatura? Quer dizer que as partículas, você imagina que elas não estão num universo de ficção separado do mundo real, mas estão no mundo real onde tem temperatura. Temperatura quer dizer que elas tem vibrações aleatórias. Então, eles adicionam essas vibrações aleatórias e então, basicamente, o que eu fiz aqui foi mais ou menos o desenvolvimento histórico do algoritmo Metropolis-Hastings. Você começa resolvendo a EDO de maneira numérica.
Tentaram modelar deterministicamente.
Não dá certo. Aí botaram um ruídozinho. Aí viram que isso começa a dar certo, só que para implementar é complicado, porque você tem que transformar em linguagem de máquina, e ainda na segunda simulação ainda tem espaço físico. E aí o terceiro passo foi passar para bits, não? E aí quando você representa o espaço físico por sequências binárias, o que acontece é que essa sequência binária, se você quer transformar no espaço físico, você tem que dobrar ela. E tem interações de longo alcance, porque esses dois pontos estão perto no espaço real, estão longe no bit. Então, aí é que entra o G e J, mais ou menos. Então, isso aqui, mais ou menos um desenvolvimento mais ou menos histórico. E aí, bom, então vamos fazer geral. E aí apareceu o Metropolis-Hastings. Esse aqui é o Metropolis. O Hastings do Metropolis-Hastings é essa generalização aqui. Mais ou menos, essa é mais ou menos a história. Bem simplificada. So, this is not the only choice, okay? There is another choice that I like more, which is the so-called Glauber. And in Glauber, I'm just going to write Glauber for this one. So because you see that, okay, so let me write here C, no? So the final C, no? Is equal to 1 if V prime, sigma prime is smaller than V sigma, and it's equal to the exponential of minus beta V sigma prime minus V sigma if V sigma prime is bigger than, well, less or equal, bigger or equal than V sigma. Okay, so this is the C. And now, there is another choice which is called the Glauber. Glauber algorithm, which is the following. In Glauber algorithm you do exactly the same, but you define sigma, sigma prime in a different way. Okay, so let me see if I remember it correctly. I think this is the one. Okay. So what is the difference? Okay. So this one, if you check it, so you see that this is a function of the quotient mu sigma prime divided by mu sigma. Okay? That this function here is a function of this ratio here. And the function is the following. It's like this. This is the so this is Metropolis. So this is Glauber. So you see that Metropolis is more efficient. So Metropolis is more efficient than Glauber, but Glauber is smoother. Because this function, the rejection function for Metropolis is not smooth. No, it has a corner here. This one is smooth. For the mathematical aspects of the chain, this one is easier to analyze because of the smoothness. So in general, people work with the Metropolis function. This is what people do. Because, if you are actually running an algorithm, you don't care about proofs, no? Or how difficult are the proofs. You just run the algorithm. And this one is better, no? It's better by a factor 1/2. It's not that much better. But sometimes, if you really want to make proofs, you go to. It's easier to consider the Glauber, because the Glauber is smoother. So, for example, no. In these algorithms, so at some point I told you that this is like a gradient descent, no? So you actually want to show that these algorithms converge to a stochastic gradient descent. That proof is easier to do with the Glauber rate than with the Metropolis rate. Because of this kink, the Metropolis is not always smooth. What actually happens is that when you run the simulation, it's very unlikely that you're going to hit this region here. So at the end of the day, it's the same thing. But, well, if you are interested in proofs, Glauber works well. Very good. So this is the famous Metropolis-Hastings algorithm. If you think about it, okay, so I told you at the beginning about the domino, right? So now you can try to think about this algorithm for the random domino tilings in terms of the Metropolis-Hastings, and you will see that in the case of the random domino tilings, there is also rejection algorithm, and the rejection function is actually deterministic. No? What happens is that you reject in a new sample if you choose a square which is not a 2 by 2, is not the union of two dominoes. So we are also doing rejection sampling, but with a deterministic function. So in terms of metropolis hasting, is a very simple one, because we don't need to do the step B, no? Because the function C is always equal to 0 or 1. So you go directly to step C. So, okay, so this is Markov chain Monte Carlo. So it's a super let's say adaptable idea, and that's why it's so popular as an algorithm, because if you think about it, all these problems are very different one from the other, no? Sampling a domino tiling, trying to find the minimum of a function, trying to compute the integral of the volume of a certain domain. All those problems are very different in nature, and all of them can be actually attacked with the same idea, which is this Markov chain Monte Carlo. And the idea is the same. No? Okay, how do you do it? Well, run a Markov chain which has as invariant measure the target distribution, and that's it. Why that is a good idea? Because the running time of these algorithms are usually slow. Are usually polynomially slow, which is actually good, because they are not exponentially slow. And most of the deterministic algorithms, they are polynomially fast. They are very fast, no, in terms of the polynomials, the degree of the polynomial of the convergence, but they get exponentially slow with dimension. And these algorithms are basically insensitive to dimension, and they kind of slow if you do it in low dimensions. But as you mount in the dimensions, they don't get worse. Very good. So I think that's it for today. So we still have Tuesday, no?